And again, you can find it on these PowerPoint presentations. I'm just going to skip to that part to show you where we start.
My computer is so slow.
This one right now is actually quite responsive. I'm surprised.
Which slide are we starting with?
I'm going to start with that one just because it's the one that I use on Monday. So I'm going to copy this formula to the board. This formula happens to be a compound found in pairs, and it has an interesting name, propyl acetate. It doesn't matter what the name is. What we need is this formula. So I'm going to copy it here. Because what we're going to talk about is something called mass percent composition. And it's actually useful if you're going to study chemistry beyond this course. If you're taking chemistry just because it was a requirement to another program, this is going to be a good mental exercise, but it's not going to be something that you're going to use a lot. So it's going to make you think. It's going to help you exercise your brain. But it's not exactly something, extremely useful if you're not a chemist. So this chemical, and I'll put the name here just so that we can call it something rather than reading the formula. It's called propyl acetate, and it has this chemical formula. Now, at this point in the course, you should know that, let me just make sure that this is taping. Yeah. You should know that this chemical formula tells you how many carbons are in 1 unit of this, how many hydrogens are in 1 of these, and how many oxygens are in 1 of these, right? That's what those numbers indicate. So when you read it, and that's what we covered last week, you say 1 mole of C5H10O2 has 5 moles of carbon. It has 10 moles of hydrogen, and it has 2 moles of oxygen. So that's what the formula tells you, right? This is review from what we did last week. What we're going to try to do now is, using the mass of each of these guys, calculate how much of this formula of propyl acetate is carbon in percentage, how much is hydrogen, and how much is oxygen. And it would be very nice if all I would have to do is say, oh, well, it's 5 divided by the total of that. But that's not what it is. Mass percent composition is based on the molar mass. And what is the molar mass? Is the masses of each of these added together, as we learned last week. Now remember that you can Google this. You can actually say, what is the molar mass of C5H10O2? And you'll get an answer. But you should remember that we know how to do it. So the molar mass of that molecule is going to be 5 carbons. Sorry. It has 5 carbons multiplied by the molar mass of 1 carbon. Now, the molar mass of 1 carbon in the periodic table is 12 point something. I'm just going to use 12 to make things easy. But that comes from the periodic table. You look at the periodic table. and you look up the molar mass. But again, I'm just going to use 12. So you see, 12.011. To make things easy, I'm just going to use 12. Then we have 10 hydrogens in here. So we're going to say 10 H's times the weight of each hydrogen. I'm just going to use 1. Although it's 1.008, if I click there, you can see it here, 1.008. Instead of using that, I'm just going to use 1 to make things easy. Because we already know how to do this. We learned it last week. This is a quick review. And then you have 2 oxygens. 2 oxygens times the mass of oxygen is 15.999. I'm going to use 16. I'm not rounded off. So when I add these guys together, so let me show you the oxygen so that you know that is 15.999. I'm just saying, okay, I'm going to go with 16 to make things a little bit faster. So now I had to do some arithmetic here to get the grand totals contributed by each one of these to the molar mass of the entire chemical. So 12 times 5 is 60. 1 times 10 is 10. 16 times 2 is 32. If I add them all together, I get 2, 7 plus 3, 10, 102. The units of these are grams per mole. Now, if I were to look up using the internet for the molar mass of propyl acetate, molar mass of, and I'm just going to put very simply C5H10O2, and I'm going to hit enter. There it is, 102. That's what we said it was. Now it's a little bit more because I rounded off. So I didn't go precisely, but that's fine. The point of this is that you know how to calculate molar masses. So we're going to start now with this idea of mass percent composition. So now that we know the molar mass of this compound being 102 grams per mole, percent is always defined, as you know, as parts divided by total times 100, right? That's percentage always. So parts total times 100%. So we're going to calculate the percent of carbon in percent. And what we need to use is these parts, not the number of atoms, but the molar mass contributed by each ingredient. Okay? So carbon contributes 60 grams per mole to the molar mass of this whole thing. Therefore, the percent of carbon is going to be 60 divided by 102 times 100. That's going to be how much carbon we have in mass. Then we'll do the same for hydrogen, the percentage of hydrogen. But of course, for hydrogen, we're going to use the parts of hydrogen, 10. So 10 divided by the total times 100. So now you guys tell me what to put for oxygen. What do I put for oxygen? How do I calculate the parts of oxygen?
32.
So it's going to be 32, the contribution of oxygen. This is not a 0, this is an O. Let me move it a little bit over here. So 32, yes, the contribution of oxygen divided by what?
102.
By the grand total of the molar mass of the entire compound, 102 times 100. And that's it. So if we do the arithmetic, and I'm going to need a calculator here. Uh, 60 divided by 102.
Times 100 is 50. I got 50.
58.8? That what you got?
I got 50. Hold on, I could be doing something wrong.
Okay, please repeat it. 60 divided by 102 times 100. And we're going to report this to 1 decimal point. I get 58.8.
Yeah.
Okay. 58.8% carbon. That's how much carbon there is in propyl acetate in mass, in grams per mole. So we'll do the same for this. Ten divided by 102 times 100 is 9.8. Percent hydrogen. Even though there's a lot of hydrogen in number, you see how you have 10 here? The contribution is less because it's a very light element. It has a molar mass of only 1, as opposed to carbon, which has a mass of 12. And then finally this one, 32 divided by 102.
I rounded it off, so I got 31.4.
Okay, let's see if that's 31.4. You rounded it up correctly. 31.4. Oxygen. Now, notice this. If we add these three numbers together, we get 100%. So 58.8 plus 9.8 plus 31.4 gives me 100%. But importantly, you just learn how to calculate the mass percent composition of a very complicated formula. And to test your understanding, I'm going to give you a simpler one and ask you to calculate the mass percent composition. Now, let me show you once again how this actually can be done by just going to the internet. I don't know if this is going to work the way I'm going to put it, but I'm going to give it a try for the first time ever. I'm just typing mass percent composition of C5H10O2. It may work, it may not work, I don't know. But we have a reference to see if it worked or not. Well,
It gives the 3. Yeah.
31.3% carbon, we calculated 31.4%, so right on the money. 9.9, we said 9.8. 58.8, 58.8, that's what we said. So it does work asking a simple engine. Better than that, I would go to Wolfram Alpha to double check my answers. And here, I'm just gonna type C5H10O2, nothing else. I'm not gonna ask a question, I'm just gonna type that, see what happens. This is an engine that is for science, so it knows that this is a chemical. So, what is it telling me?
The molar mass is 102.1.
Right. So it's telling me the molar mass, which we calculated before. And down here, elemental composition, mole percent, mass percent. This we're not doing in this course. We're not going to do in this course. That is simply, like I said before, 5 divided by the grand total of atoms. Don't worry about it. Please erase it from your head. Mass percent is what we're doing in this course. 58.8, 9.9, 31.3. That's exactly what we have. I mean, we don't have these numbers because we rounded off over here. We did it to save a little bit of time. But there it is. It gives you the information that you need. Of course, you need to know that you ignore these. You go to mass percent. We're not talking about mole percent in this course. I mean, mole percent is a heck of a lot easier. Where this came from, it came from 5 plus 10 plus 2 is 17. 5 divided by 17 gives you that. 10 divided by 17 gives you that. 2 divided by 17 gives you that. But that's not what we're doing. We're doing only mass percent. So now, you guys had to prove to yourselves that you know how to do this. And this time I'm going to give you an easier molecule. One that actually shows up in a problem. So I'm going to leave the backbone here. And I'm going to give you a different formula. So let's start easy. Calculate the mass percent composition of that molecule. What is the mass percent composition of H2O2, hydrogen peroxide? We're not going to need carbon. We're just going to need those two. So the first thing, you need to get the molar mass, right?
Correct. So you would do 2 times 1 for hydrogen.
So we had 2 hydrogens times 1. You got it. And?
Then you do 2 times 16.
Yes.
Round it off.
Yes. That's exactly what you do. 16. 15.999. Should we do it exactly this time? Let's do it exactly. 1.008, 15.999. Why not? I mean, it's an easier one. Just so that you know that rounding off doesn't take you too far away from the real calculation. Great. So now we just do the math. 2 times 1 is going to be 2.016. This one is going to be Oh my God. 31.998 maybe?
31.998.
Yeah. So, and then how do we get the molar mass?
Add the two together.
We add the two together, exactly. So 14, 2, 11, 0, 3, 4. I come up with 34.014
Correct.
grams per mole.
Correct.
All right. Now how do we get the percent mass composition? What do we put where?
Put 2.016 where hydrogen goes. Oh, actually, no, yeah.
No, you got it, 0.16. And what do I put on the bottom?
34.
Thank you. Beautiful. And then what about here?
31.998.
Uh-huh. And I assume that since you told me that was there before. Okay, so let's do the math, and then we're gonna ask Wolfram alpha. What happened to my calculator? It went away. $2.016 divided by 34.014. We're just gonna do one decimal place. So 5.9 is what I got here. Does that agree with what you get?
Yeah, I was just writing it down, just taking an extra note. Sorry.
Oh, yeah, no, go ahead. Take all the notes that you want. You got a different number?
I did it wrong, that's why.
Oh, God, don't know. I could have done it wrong myself.
Divided by 34. Okay, so that does equal 100%.
Great.
I just double checked the two numbers and added them together, and I did get 100%. So
Perfect.
5.9.
And the other one?
It'd be
I got 94.1.
yeah. I get 94.0.
7.
Yeah,
So only one decimal point,
just 94.
94.1. If we do it only one decimal place. And if we add those two together, we get 100. As expected.
Is it always going to equal 100?
Always. Unless you made a mistake.
Then you made a mistake, right?
Unless you made a mistake, right. So that's a good checking point. If you, and of course you have to consider the fact that you need to do every element in the formula. If you leave one out, if this one had carbon and we leave it out, then it's not going to add up to 100.
Mm-hmm.
Now let's ask Wolfram alpha. So we're gonna go back to Wolfram alpha, and this time we're gonna put H2O2. And hit enter. It gives you the name, hydrogen peroxide. It gives you the mass, molar mass, exactly what we got, 34.014. And then let's see if it gives them the mass percent composition. Last time we did get it, but this time it doesn't seem to be giving it to us. So, wolfram alpha, sometimes you have to be a little bit more specific. It's not giving it to us right here. So let's see, more. No. I don't see it. So I have to ask, molar H2O2 mass percent. Oh, now we have it. 5.9, 94.1. That's what we got. A group of chemicals known as the hydrocarbons. There's a lot of hydrocarbons out there. Many of them are really bad for your health. You don't want hydrocarbons on your food unless you're dealing with fat. Fat is a hydrocarbon, but it's not a bad one, it's a needed one. The name hydrocarbon should tell you as to what the composition of these chemicals is. So gasoline is a mixture of hydrocarbons. So what do you think a hydrocarbon compound is going to have? Name 2 chemicals that you think hydrocarbons are going to have. Well, look at the name.
Carbons?
They're going to have carbon, and what else?
Hydrogen.
And hydrogen. That's it.
No, I was thinking hydro was in water.
Right. Hydrate, means water.
Right.
So you were right, but it's
But I'm not.
hydrogen in this case.
Right.
So no worries. I mean, when you look at the word hydro, you immediately think water, yes. In chemistry, hydro means hydrogen. So hydrocarbons have carbon and hydrogen. Now, there's thousands of hydrocarbons. Thousands. I'm going to show you here the simplest of all. There's no simpler hydrocarbon than this chemical. Okay? This chemical has a name. It's not part of the problem, but it's the simplest hydrocarbon of all. It's called methane. And you probably have heard that name. If you haven't, I'm telling you, this is one of those gases that is contributing to global warming, to climate change. But the point here is that it has 1 carbon and 4 hydrogens in 1 unit. Now, this is not an ionic compound. This is a molecular compound, meaning carbon is in group 14. Remember that? So carbon doesn't like to give electrons away. It doesn't like to pick up electrons. It likes to share them. How do we show that in a formula? Because we don't have ions. We don't have plus 2s, negative 2s, negative 3s, positive 3s. We show it very simply as this. We put carbon, and then for every electron that carbon is sharing, we draw a dash. So carbon has 4 electrons, right? It's group 14. So it's sharing 4 electrons. So a dash doesn't show you 1 electron, it shows you 2 electrons. 1 belonging to the carbon and 1 belonging to the other atom that is sharing with carbon. In this case, the partner of carbon is hydrogen, and there's 4 of them. Okay? So 1 carbon is capable of sharing 1 electron each with 4 different hydrogens. So methane, with this chemical formula, can also be written like that. It's the same information, except there's a little bit more detail here. Now, this is the simplest hydrocarbon, but there's many more. What would you say is the next logical simpler hydrocarbon. Not as simple as this, but a little bit bigger. What would you say is the logical progression?
Could go either way. It could go C1 something, or it could go H5 something.
Not really, because the relationship between carbon and hydrogen has to be
Right.
just like this. So we're going to ignore the hydrogen and just look at the carbon. So this has one carbon, right? What's the next possible complexity? What comes after 1? It's not a trick question. What? Start counting. 1, 2. So the next chemical would have 2 carbons. That's the next hydrocarbon. Now, because that is true, and because this is true, I can actually write carbon and carbon joined together, sharing an electron pair, and those are my 2 carbons. The problem is that carbon needs to share electrons with more atoms. And in hydrocarbons, the other atoms are hydrogen, always. So everything else here that is needed to give each carbon 8 electrons, or 4 bonds, just like here, 2, 4, 6, 8, 2, 4, 6, 8, are hydrogens. So hydrogen, 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 and hydrogen. And that's the second hydrocarbon that exists. Now, can you please count the number of hydrogens so that I can put it on the formula?
6.
There's 6 of them. 1, 2, 3, 4, 5, 6. Thank you. Now, don't worry about the name, but I'm going to give you the name just because it does exist and it shows something of a progression. It's called ethane. Okay, now that you're on a roll, what would be the next one in complexity?
C3.
Yes. We're just going to add 1 carbon at a time, making it bigger, 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 starting from the simplest one to get more and more and more. Okay? Now, I'm going to start with the C3. I'm going to put them this way, this time over here. So 1 carbon, 2 carbons, 3 carbons. That's the C3. Now remember what I said earlier for these 2. Each carbon needs to have 4 dashes because it has 4 electrons, right? So 1, 2, 3, 4. Then for this second carbon is 1, 2, 3, 4. For this carbon, 1, 2, 3, 4. Every carbon has to have 4 dashes because it comes with 4 electrons. And even though you see here this dash being part of this carbon, it's also part of this carbon. That's the sharing. It doesn't belong to one, it doesn't belong to the other, it's a share. But every carbon in here has 1, 2, 3, 4 dashes, which means 8 electrons, because each dash is 2 electrons, 1 from each carbon. Now, the rest in a hydrocarbon has to be hydrogen. There's no other way. So how many hydrogens are we going to put? 1, 2, 3, 4, 5, 6, 7, 8. So the next part of this formula goes like that. And it has a name. This you may have heard, propane. Some of you actually have propane stoves at home. I have a propane stove at home. So this is what I'm burning at home when I cook. When I turn on the gas, this is what comes out. Okay. Do you see a pattern in the naming? Is there anything that the 3 have in common?
Yeah, they have the same ending.
All of them end in A and E. So when you have hydrocarbons with single bonds and only hydrogen, you have compounds that end in A-N-E. They're called alkanes, but don't worry about the name. Just be sure that all of them are going to end in A-N-E. So let's see if you can predict what's the next one. C4. Now, I'm going to put the H here, and look at the pattern of the hydrogens. We went from 4 to 6, from 6 to 8, and you got it. It's going to be H10. And if we draw it, you're going to see that that is in fact correct. 4 carbons, 1, 2, 3, 4, right? So each carbon has to have 4 dashes. 1, 2, 3, 1, 2, 1, 2, 1, 2, 3. Now if we put hydrogens there and count them, we do have indeed 10. All of a sudden, you just came up with a predictive formula. Look at what is happening. As we increase the number of carbons, we're increasing the number of hydrogens by times 2 plus 2. So 1 times 2 is 2 plus 2, 4. 2 times 2 is 4 plus 2, 6. 3 times 2 plus 2, 8. So I can actually write Cn, where n is any number. It can be 1, it can be 5, it can be 20. And then H, and it's going to be 2 times n plus 2. 2 times n means 2 times this number, right? So let's see if that is in fact the case. I'm going to put here C10. I skipped a bunch of them. So if n equals 10, what is going to be hydrogen?
14.
So 2 plus n, which is 10, is 20.
Wait, huh? Oh, 2n.
2 times n.
Oh, okay.
N is equal to 10.
Right.
So 2 times n is 20 plus 2,
It's 22.
yes. And that's for real. Now, you don't need to memorize this, of course, but it's very useful because you can write the chemical of any of these without having to draw all of these huge molecules. Now, the name of a hydrocarbon with this formula has to end in A and E. After this one, I didn't give you the name, but this is called butane. After butane, it's really easy to name them because you use the Greek prefix that means a number. Penta in Greek is 5. Hexa in Greek is 6. Hepta, 7. Octa, 8. Nona, 9. Deca, 10. A decade has 10 years, right? So deca. So this guy is actually called decane.
Oh, deca 10, 19.
Yeah, deca means 10 years, so decade rather. So deca means 10. And decane means a hydrocarbon with 10 carbons. So if we go back to the problem and we look at the names of the chemicals that they are giving us as part of the problem, you're going to see that all except one end in A and E. And I'm going to put them on this side now that you know how to predict them. So this was a mini lecture in organic chemistry, something that you probably will not have to take, but I think is a useful. So here are the hydrocarbons that are part of this problem. Hexane means 6, heptane 7, octane 8, nonane 9, decane we already have there. So hexane, it would be C6, H what?
14.
Yes! 6 times 2, 12, plus 2, 14. So this is, so the next one is heptane. Hept means 7. I just happen to know that. So what's going to be the formula? C7 what?
16H.
Absolutely. Yes. 7 times 2 plus 2. Octane. Octa means 8. So H what?
18.
Yes. And then let's put the last one, nonane. Nonane means 9. So C9, H20. 9 times 2, 18, plus 2, 20. Decane, we already have it over there. So what they want is, in this problem, they want you to write, and this is key, you guys, balanced chemical equation for the complete combustion of the hydrocarbons. So let's break that apart. What does that mean in plain, simple English? What does the complete combustion of something means? So here we have a new word, combustion. Now some of this is actually chapter 8 already, but we need it for wrapping things up as far as balancing equations. Have you ever heard the word combustion before? No? Your car, when you put gas in it, if it's a normal car, and you start driving it, if you have a car, is combusting gasoline, is burning gasoline. When you put wood in the fire, you know, whether you or charcoal on a barbecue, you're doing a combustion. So all combustions look like this. You have a fuel. You guys know what fuel is, right?
Right.
Charcoal, gasoline, whatever. And you need oxygen. You need oxygen. So all combustions are going to have a fuel and oxygen. This can change. It can be many different things. This one is always oxygen. That doesn't change. All combustions are going to produce the same result in just different amounts, regardless of what you are burning. This is burning something. Okay? Combustion means burning. What are the products? What is the outcome? What is the resulting of that burning? It's always going to be carbon dioxide, and it's always going to be water coming out. Always.
Of that equation only.
Of any burning of anything. When you burn wood, you're using oxygen with the wood, and after the stuff is burnt, carbon dioxide is being released and water is being released. Plus energy, of course, you know, the heat that you feel. But that we're not going to put here. Now, this is a chemical equation. Chapter 8 is about chemical equations. You have something, then an arrow, and then something. Okay? All chemical equations have an arrow. They have something before the arrow and something after the arrow. Now, what happens if the fuel, we know what it is? Well, let's put it here. Instead of fuel, we're going to use, what's the first problem? What is the problem in your question?
Liquid nonane.
Nonane?
Nonane, sorry.
Okay, liquid nonane. So this is it. That's what we're going to put here now as the fuel. So we're going to put, what happens when I burn C9H20 in the presence of oxygen? I'm sorry, I probably need sugar now. C9H20, nonane, plus oxygen, carbon dioxide, and water. Well, part of this problem is doing something called balancing an equation. This equation, as written here, has the right formulas. This is the correct formula for nonane. This is the correct formula for oxygen. That's the correct formula for carbon dioxide. And that is the correct formula for water. All combustions have that, and that fixed. So we have to have the right amounts on both sides of the equation for this equation to be correct. Otherwise, it's wrong. So I'm going to ask you a question, and please think carefully. Before the arrow, on this side, how many carbons do you see?
9.
And on this side, how many carbons do you see?
1.
1. We have to fix that problem. In fixing that problem, we cannot change this formula. It has to be CO2. We cannot change that formula. It has to be water. It has to be H2O. We cannot change that formula because that's what we're burning, and we cannot change that formula because we're using oxygen. The only thing we can do is change the amounts. So we can have a number in front of this, a number in front of here, a number in front of here, and a number in front of there. Now, what number? Well, that's what you are doing to solve the problem. You need to figure out the number.
I don't know why, but I feel like I've seen this before, but...
Well, because we've done it before. So here we go. What numbers am I going to put here so that I have the same amount of each atom on both sides of the arrow? Well, let's start simple. Let's start with the carbon. We already know that I have 9 carbons here, right?
Right.
Can I put a number here that will give me 9 carbons? I have only 1, so what do I have to do?
Add 8.
If I add 8, that means 1, 2, 3, 4, 5, 6, 7, 8, right? That's what you're saying. Add 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, but I have 1 here already. So it's 8 plus 1.
Give you 9.
So it has to be a 9 there. You just told me add 8. No, add an 8. If I put an 8 there, if I put an 8 instead of the 9, I have 8 carbons, not 9. You told me add 8. Well, I have 1 plus 8 gives me 9. Right? So now I have an account to check. I need to check this counting. I have 9 carbons here before the arrow. I have 9 carbons here after the arrow. 9 carbons and 9 carbons. Let's do some accounting because we need to make sure that everything is accounted for. Now here's the thing. There's only one way of doing these problems, and that is by trying something, and if it works, it works. If it doesn't work, you have to try something else. It's called trial and error. You're going to be making mistakes, and you're going to fix them. And you're going to make mistakes and fix them until you get to the right answer. And it may take you 5 minutes, or it may take you 1 minute, depending on how complex the reaction is, how easy to balance it is. But do we agree that now, by putting a 9 there, we did not change CO2, we just have 9 of those, and now we have 9 carbons and 9 carbons, right? Let's count the next element. What is here? Hydrogen, right? How many hydrogens do I have on this side? Hydrogens?
Wait, hydrogen's on this side or that side?
No, on this side. 20. 20 hydrogens on this side. How many hydrogens do I have on this side?
2.
Only 2. So there's the hydrogen is not balanced. I need to put a number here that will give me 20. 10. 10 times 2? Now we have 20 by putting a 10 in front of the H2O. Let's go back and review. We have 9 carbons. We have 9 times 1, 9 carbons, right? We have 20 hydrogens. We have 10 times 2, 20 hydrogens. Beautiful. We balance the hydrogen, but now we have to count oxygen. We're not done. How many oxygens do we have on this side of the equation total?
2.
Only 2 oxygens, 2 oxygens. And over here now we have a lot more because we added numbers. So how many oxygens do we have on this side of the equation total?
2 oxygens and 1 on the other side, right?
Yeah, but this 9 right here affects the whole thing. That 9 means that you have 1, 2, 3, 4, 5, 6, 7, 8, 9 CO2s. How many oxygens are here? 2, 4, 6, 8, 10, 12, 14, 16, 18. 9 times 2. 18. But we're not done. We also have high oxygen here.
Oh, shoot, and that's another 10.
Right. So 18 plus 10?
18 plus 10 is 28.
So we have 28 high oxygens on this side, but only 2 on this side. How do we fix that?
But that one's easy because we have O2 by itself.
Because we have O2 by itself, that one is easy. You got it. So what number multiplied by 2 is going to give me 28?
Oh, wait. What's half of 28? 14.
14. So how do we enter it? Well, we're going to enter exactly what we have there. So we're going to type carbon. Now watch this tool that I'm going to use. I'm going to click right here and use the subscript, the XB, to put the 9. Okay? So C9. H20. I need to go back to the top, not where the 9 is. So click anywhere else, put the H, and then click on the subscript again, and put the 20. Then click anywhere else, and then you're going to put parentheses, lowercase l, that's not a 1, that's actually an L, and close parentheses. So that's the first chemical, this one. Okay? Are you putting them in there? Okay. Now we're going to put a plus sign because we're combining that With what? With oxygen. So capital O, don't put a 0, because if you put a 0, you're going to get it wrong. It has to be a capital O for oxygen. Lowercase 2. I missed the first number. It's 14, right? I had to put the 14 there in front of the O2. Now, this is not nonane, but that's what you are entering on your problem. And then a parenthesis G for gas, because you have to include the state of matter. They want everything there. So far so good. That's the reactant side of the equation before the arrow. Where is the arrow? Right here. Okay, just click on that single arrow once, and it puts it there. And then I have over here 9CO2. So I need to put a 9. C, capital O, and then subscript 2. I need to put that is a gas, so parentheses G, close parentheses, and then a plus sign. And finally, I have 10 waters, 10 H2O, 10 water, H, subscript 2, capital O, or he's going to mark it wrong, not 0, and then parentheses G for gas. And
H2O is gas?
water is always a gas, yes.
Oh.
Because there's heat. You're burning this stuff.
Oh, okay. So it's the
So it's steam.
Okay.
It's coming out as steam. Now, I'm not going to submit it because this equation is for nonane. Here is octane. So it's going to mark it wrong. Okay? What do you have on yours, Amanda? The very first one.
I had octane, but we did that one
Okay.
last time.
But if you have nonane and you enter this, I want to see that it marks it right and it's going to give you background. It did. And it gives you all of this information. Mm-hmm. Okay?
Yeah.
It's a lot.
Yeah.
It's a lot. Yeah.
The only part I think I'm really gonna struggle with is just the numbering.
The balancing part.
Yeah.
Well, but you're not going to struggle if you practice. I mean, you got, of course, no pain, no gain, right? That's the saying. So when you say struggle, I hope you mean pain.
Yeah.
Not that you're not going to be able to do it. Because you have a guide, it's just going to have to be. And now, by the way, you're not alone on this. On Monday, we're going to come back and we're going to continue with the chapter 8, which is going to be a lot of this stuff. Okay, so that's the end of chapter 7.